Well, thank you very much. Good morning, everybody. This morning, what I'm going to be talking about is a TxDOT repair or retaining wall repair project that was recently completed in this past spring, spring of 2015. It was the repair of a couple of voided out sections of a dry stack retaining wall that was deemed to have historic significance. It was built approximately 80 years ago. And in the time that I have today, basically what I'm going to do is provide a general overview of project timeline, essential decision making, and key design considerations, as well as challenges faced in construction and then how they were resolved. And so also I should have time for any questions that you may have at the end. And so just to give you a little bit background on this project is located on Highway Texas 290, which is just south of I-10, as you can see here with the pin on the screen. It's about 90 miles southwest of the city of San Angelo. And it's a remote area about 10 miles east of the town of Sheffield, which is actually at that junction just to the left of the pin. And like I said, it's a fairly remote area, so that factored into a lot of the decision-making process on this, which I'll actually get to soon. And the contractor was actually very forthcoming in addressing any potential safety issues that could have occurred by acquiring a satellite phone, as cellular service was fairly spotty in that area. It's just to give you a little bit of background on the initial construction of the wall. This is actually a pretty cool picture from when the wall was being constructed in roughly the 1930s. As you can see from this picture, this is the dry stack wall portion here. That essentially how the dry stacking works is you take large rocks, almost boulder-sized rocks, and intertwine them and interweave them so that they actually behave as a solid mass rather than fairly small individual elements. And also, as you can see from this, in this area, that they actually dug out behind the wall and in front of the wall in order to put that rock in order to construct it. This wall is approximately 10 to 25 feet in height and around 400 feet in length when it was constructed. A little bit more background. This wall is classified as a gravity wall, and as you can see on the right, there's just a kind of a sketch of the cross-section there. And by a gravity wall, it relies entirely on the self-weight of the stacked rock to resist any lateral loading and satisfy external stability. The wall face is battered back, as you can see from the picture there, and this is done to stabilize the face of the rock so you don't have any rock falling off the front. And however, one of the drawbacks of this is of this type of wall is it's fairly sensitive to erosion, so any weathering or loss of material from the rock can actually result in voids and material moving around, which is actually what I'm going to be talking a little bit more as we continue through the presentation. And so I'm getting into the project now. Today, the San Angelo District contacted Bridge Division in spring of 2014, so about a year and a half ago. And after a significant rainstorm, they said they had found two severely voided zones spanning 55 linear foot, which is actually the one shown in the picture. It actually extends a little bit further this way outside the edge of the picture. But that's that portion there. And then there's actually another one about 300 feet down on the other end of the wall that's about 33 linear feet in length. And as you can see from this picture, the barrier has been undermined almost completely, and actually you can almost see up to the underside of the asphalt behind the barrier there. And actually the rock on the surface, even the rock here in the front, shows signs of significant deterioration. And this is actually a little bit of a closer up picture of that same exact portion. This picture was taken approximately 6 months after the previous picture that I showed you, a little bit closer to the time of construction. And as you can see, the weathered rock in this area has almost turned to a gravel or cobble in this area. And you can see that you can actually see a little bit of daylight up there between the pavement and a little bit of the asphalt in front. So this problem had deteriorated and gotten a little bit worse over time. And here is actually just a quick picture of the smaller of the two weathered areas. It's actually right in this area here. However, it was fairly difficult to get a picture closer to us because actually the slope in front of the wall is fairly significant and difficult to traverse, which actually factors a little bit into some of the construction considerations as well, but it's in that portion right there. And so actually the retaining wall below, as you might have imagined, caused a significant deal of pavement distress right above the wall, and that's pretty much taken at the same time as the picture 2 slides ago, where the failure had resulted in daylight right here. And so it resulted in fairly significant pavement and barrier distress. And as you can see on the right side of the picture on the right side of the slide here, that you've actually got a barrier dip in this location, and then it's a little difficult to see, but you've got another one in that location, and that coincides with the two failure zones that I just spoke of. And so as a result, as a result of what we found, the decision was made to put traffic control measures in place. And so all the two-way directional traffic of the two-lane road was actually placed into one lane, the lane furthest away from the wall, and a signalized system somewhat similar to like an automated flagger somewhat was put in place to actually handle traffic control through there. After review by the district, this project was decided to be let as a routine maintenance contract, and this was generally done because actually, as you can imagine, this road wasn't it wasn't handling too many vehicles at one time. So actually, the vehicles per day was fairly low, and so it didn't have a profound impact on traffic traveling through there, and so an emergency contract wasn't necessary. And so now I'm going to get into a little bit of the design considerations of this. One of the big things that we were considering in coming through to design this was actually preserving the historic value of the wall. Both the barrier and the retaining wall had been deemed as historic structures. And so the main consideration here is to make sure that we keep as much of the barrier and the retaining wall in place as possible. And so with that in mind, as you can see from this picture, weathering and deterioration was present throughout the wall. It wasn't something that was fairly isolated to the areas that we're talking about, the voided portions. It was actually fairly common throughout the wall. And so with that in mind, we decided to actually treat the entire wall with soil nails, and so reinforce the entire wall to ensure that we don't have issues with voids again. And so with that, it made the most economic sense to actually cover the entire wall with a permanent shotcrete space and then sculpt it to match the original structure as best as possible. And then covering that up would prevent any further weathering from taking place and actually keep the structural soundness of the wall that's in place. And as far as for the barrier portion, what was decided to do there was actually remove the original materials of the barrier, set them aside during the time of construction, and then after construction was completed, the retaining wall, a masonry expert can actually reassemble the barrier using the original materials, and then a concrete cap on top would have to then be recast, and it would just look just the same as it did before. And so the benefits of soil nails is actually fairly minimally invasive to the existing structure. They're fairly small elements, and so a lot of the, small and fairly spaced out, and so a lot of the rock that was in place, we wanted to just keep it there because it had a structural purpose, and wanted to make sure that we didn't upset or move as much rock as we could. And so along with that, we provided the option to use hollow core bars for the soil nail anchors, and that was able to help with hole stability and actually accelerated the process a little bit too, and that's what the contractor elected to do. And from this slide, as you can see, in these pictures, these are actually the cutting heads that were used on the hollow core bars, and they're used in conjunction with the rotary percussion drill in order to cut through the rock fairly quickly. And so how we decided to handle the repair of the voided portions was to install anchors on the existing face of the voided zone, so whatever we were left with at that point. And then the nails were coupled onto in order to lengthen to the proposed wall face, and so that they were essentially the nails on the backside were projected out to where they would be on the front face, or the permanent face. And then the section was then built up by a welded wire wall to fill the voids, and then it was covered up by the permanent face in order to actually make it pretty much look like the rest of the wall did. And so getting into prior to construction, the contractor submitted a proposal to add a 2-inch flash coat of shotcrete onto the face of the wall before installing any anchors. And this was done generally to create a smooth working surface in order to work on this, as well as preventing any rock from cleaving off and having instability at the face. This shotcrete was to be fiber reinforced, and actually the fiber reinforcement had its benefits as it allowed for a better bonding of the rock that was initially there, and so we were actually able to count on it structurally and thereby decrease the footprint of the wall face on the front by, say, a couple inches. And so another concern before construction was site equipment access. And so the contractor then decided to build a temporary berm at the bottom of the wall to allow small equipment. However, a lot of large equipment had to be stationed on top of the wall. And so with that in mind, a couple of different methods were used to install the soil nails by the contractor. The first one was actually using an excavator and holding the drill and drill by reaching over the top of the wall with the excavator. And this was done using for the top few rows of nails. However, this is, in this case, in the taller portions of wall, it was a little bit more difficult to use this in that situation. And so actually what the contractor did was used what's called a wagon drill, or a frame that orients and holds the drill. And this is actually able to rappel and scale up and down the wall so you can reach almost any location. And then this was also used for the lower portion of wall, the fairly small equipment. And so now getting into the actual construction portion, the soil nail verification testing was done prior to construction, or prior to any installation of the, to the production nails, excuse me. And this is done to verify the strength assumptions that were assumed in design, and also to evaluate contractor drilling methods. We learned a couple of important things from doing these tests previously, and the first of which is that we actually didn't reach the rock material that we saw in the boring logs that we took prior to construction. And the reason why that is those boring logs were actually taken fairly far away from the back of the retaining wall, actually on the other side of the road, and it showed that it was fairly close to the surface in those locations. However, we found that the rocks, especially at the nails higher up in the wall, the rock surface was actually sloping towards the wall, and so there was actually a lot further back in the holes than we originally, in the soil nail holes than we originally expected. And so that also may have something to do with the fact that when this wall was built, it was actually excavated behind, and so that's actually not native material. And the next thing that we found was initially the test holes actually had taken about 20 times the theoretical volume of grout to fill the hole, because the grout had actually seeped into the voids through the stacked rock volume, so we were actually losing quite a large amount of grout. And so with that in mind, the decision was made to ensure at least a 5-foot minimum tag into the rock layer, and thereby adding grout at least at the very minimum 20 to 30% more than the 5-foot volume. So that involved increasing the lengths of many of the anchors that we were looking at, especially in the higher portions of the wall, like I said. And so this posed an interesting problem, actually. Now we have an unbonded portion of the nail where it's not actually being covered by grout, and so that poses a corrosion issue. However, at our request, the contractor verified that corrosion to the unbonded portion would not affect the 75-year design life of the wall, and so actually the bars were upscaled in size in order to make that work, and to work to where we were comfortable with it. And so that's how that was done. And so after all of the production nails were installed, a smaller shotcrete layer was added on top of the flash coat, and this was about approximately 3-inch cover over the studded anchor plates, and reinforced with steel, and then it was smoothed to create a smooth surface in order to work for the sculpting. And the application of a final couple inches of shotcrete layer was installed, and sculpting was completed in increments by the subcontractors doing the sculpting there, that you can see in this picture. And so that had to be done. That had to be done in increments because shotcrete dried fairly quickly. And so it was just very common to this project is access issues. The man lift from the roadway above was used to reach the top portions of the wall. And then after the concrete cured, the shotcrete face was then stained to reflect the original rock color after the shotcrete was completed curing. And that's what the picture is here on the right side there. And so just to sum up, the wall repair started approximately mid-May of 2015 and ended in it started in mid-March 2015 and ended in mid-April, so that was approximately 8 weeks. And the only delay was actually not worth speaking about much, but was acquiring water for grout mixture. However, it didn't cause any large problems in that way. And so this is actually what the barrier looked like after it was completed and reconstructed. It's good as new. And then over here is the repaired portion of the pavement. And so with this project, since it was a unique project, and it was a project that required a lot of innovation, it was essential for the contractor and the districts and the divisions to really work together to be able to handle any challenges as they arose in construction and to come up with solutions to unique problems that we didn't originally see. And so credit goes to all three of those groups for completing the project very quickly with minimal effect on the traveling public. And with that, I'd like to open it up to any questions. Yes? What's that? I actually don't have that off the top of my head. I apologize. Construction cost? Yes, so he asked about construction costs, and I can't remember. I don't have that off the top of my head. Yes? I'm sorry. What do you mean? Oh, it's just a welded wire wall. So is what material was used to fill the voids behind the wall? I believe it was a granular material used in welded wire walls fairly commonly. Actually, yes. As you can see in this structure, as you can see in this picture here, horizontal drains. Okay, sorry, I forgot to repeat the question. Yeah, it was asked what kind of how drainage was done in this case. And actually, as you can see on the slide here, there's actually horizontal drains that I believe are 10 foot installed behind the wall, and that's what was used to drain the structure. Okay. Thank you very much.